Right. So I'll give a perspective on what our experience are for that in the Philippines. The first stage is not actually just the spooky, but also how to bring the hype. Because it's spooky, people don't want to do it. So to do that, we want to put them in an excited state. To do that, we need to just give them a hint of what it could possibly do in the future. But once they're there, we need to put some cautions, discuss them the ethics of these quantum technologies later on. So if we have them right now in the Philippines, what could happen next? What would be the improvement, and what are the possible drawbacks, possibly in the government sector, possibly in terms of geopolitics around the region, and what does it mean? What would it mean for us? And later on, how do we put ourselves as the people forefront in having those protections and being responsible, and not to propagate this hype nor fear, no spookiness of quantum, just to make it just really real for everyone.
How about you, Yancho? Any thoughts?
Yes, thank you. Yeah, actually, on the first place, I would say that quantum looks like magic. It looks like magic. But on the second step, you see the math behind. You can be scary. So maybe the efficient way is to start with some basic concept about entanglement and superposition with some visual elements. Like, for example, on IBM Composer 2, when you can drag and drop gates and create your own circuits. From the moment in which you are able to create your own circuits, or to resolve a simple, to have simple solution on some task, you already you are already in the future to add a value, and it's you start to ask questions. So we can replace scare with curiosity.
Yeah, thank you. Yeah, I think one of the old adage is still true. One of the best way to learn is by doing. I have a question here for Dr. Lia. So, Dr. Lia, you pioneered the use of ZX calculus as a teaching tool, from IBM tutorials to high school courses. What are the biggest pedagogical benefits, or even possible risks, of leading with visual reasoning in quantum education, especially for learners without strong backgrounds in mathematics?
Thank you. Actually, that is like ties that question perfectly leads from the previous question, because with the calculus and more broadly with visual reasoning approaches, like we call this quantum pictorialism from an education standpoint. This in our course, I guess the direct advantage is that quantum teleportation is the first example that we introduce to the students. That's something they may have heard of, that is I guess hype of it will draw them in, but then we repeat quantum teleportation 3 times, each time adding more complexity in our re-explanation of quantum teleportation. And by the end of the course, as well as, by the middle of the course, I would say, the students really understand quantum teleportation in terms of the protocol and what's happening and related protocols that they can design themselves in quantum communication. Then this is something that what we can teach in the course. And it's very concrete. It's simple enough that we can teach the high school students and test them on it, and then see from the test results that they did well. And in fact, this was material previously only taught at the master's and PhD level through a decade-long course at the University of Oxford. So to do this with randomly selected, self-selected, but then from that pool of 1,000 high school students, like randomly selected about 50-something high school students, was really a first in quantum education. Because before that, the ZX calculus was created, like first conceptualized at the University of Oxford 15 to 20 years ago, because that was for research purposes, and it was solely for research purposes until very recently that study for the first time do it for education. So the ZX calculus is really popular and almost a household name for quantum computing researchers in a number of areas, especially quantum error correction, quantum machine learning, quantum circuit optimization and compilation, classical simulation, condensed matter, and we are even seeing in quantum chemistry. So we're seeing a lot of use of this in research. And so to give high school students be able to understand a language, which is in a lot more senses, a new language that is very powerful for understanding both the circuit model and measurement base, but even more general than that, like quantum error correction already breaks both models or goes beyond both models. And like and connect to real world research happening like on a daily basis. I think that is something that is an underexplored opportunity, and we're kind of seeing it used more in education approaches for quantum information around the world too.
Touche, Dr. Yeh. I hope we could implement that approach or strategy here in the Philippines. I would like to learn more about that ZX calculus and pictorialism. Okay, I think we have questions from the audience. Yes?
I'm sorry, I'm targeting you again here, but I just want to know more about the study. So do you like have a pedagogical kind of study, as in how effective it is if you teach using ZX calculus and without the ZX calculus to the high school students? Like, yeah, how effective it is. And then the second question would be, to what extent you can teach, like, are you stopping at quantum teleportation, or you can go beyond that?
Thanks. Okay. I might ask you to re-ask your second question after I answer the first one. But the first question, the contrast of can we do a comparative study between using ZX calculus versus using not using ZX calculus? We had to do 1 year of ethics approval in the UK to do this study. So it depends on each country and institutions what their procedure is, because this is a study with human subjects, especially under the age of 18, so minors. So there's a lot of legal restrictions. But we came to the conclusion it is not ethical to teach, to do a high comparative study at the high school level in the UK, because the traditional approach of teaching with Hilbert space formalism, with matrix multiplication and or Brocken notation, this is Dirac notation, this is not something that is being taught in the UK, because only 10% of UK high school students even learn matrices and to the extent of being tested. And then the national data for England and Scotland shows that the students really did badly. And these matrices become exponential size with the size of quantum circuits. So this is not something we could ethically do. If we had two groups, and a group that did not learn ZX calculus, we did not have confidence, like the hypothesis being that they will not succeed. That's not something we could ethically do. So that's my answer as to why we couldn't do this in the first study in the UK, but it could be possible for other countries which do teach matrix multiplication mechanics in the high school level. That may be possible to do some kind of study, maybe more at the undergraduate or graduate level, that would be more realistic. So it's something we're interested in, but for the aforementioned reason, we did not do it in the UK high school study.
Okay, thank you, Dr. Yeh. I have a question for Dr. Whei. Now from quantum education, now let's go to quantum science communication. So Dr. Whei, you work across hardware, software, and application teams at the NCQH. So can you paint us a picture of how you tailor your quantum communication approach when speaking to, like, for example, policymakers, industry partners, students? So those are different levels of maturity, each of whom have different stakes and technical depth.
I think overall is quite a challenging problem, because everyone has very different backgrounds. But the approach that we generally use is we want to try to find a common ground from what they're interested in. For students, generally it's quite easy because we work in a university, so there's quite a lot of a common ground that we can talk about in terms of teaching quantum and stuff. For companies, it also depends, right? If you talk to a quantum company, that's also much easier. We have a common language that we can share and discuss. Then when you talk about the non-quantum domain expert companies, such as the bank, logistics companies, that's where the first challenge comes in, because at the end of the day, a lot of the companies, at least those that I interacted with, they are only interested in quantum as far as does it affect my bottom line, and how long will it take for whatever that we are doing in quantum computing to affect our bottom line? So that's kind of like where we will base our starting point here. Number one is to, I would say we would generally try to avoid hype, and we don't promise what we can't deliver. And number two, working backwards from that, we will always say what are the type of projects that you're interested in, and then we can maybe slowly work backwards and what's possible in quantum computing today and how does it scale over the next few years. So I guess the short answer is, to summarize, is you find what they're interested in and then you work backwards from there.
Yeah, thank you for that, Dr. Whei. Basically, you really, these different stakeholders you'd approach them with different according to their needs. Anyway, I think we still have time for one more question from the audience. Yes, please.
Great, thanks so much. I think as a fellow educator, there's an interesting question we have to ask ourselves in the educating space, and that's how much space are we taking up with quantum education, and what's the trade-off here when we take space in a high school curriculum to teach quantum or whatever we label quantum, what kind of content does it actually replace? And I would be interested in your each of your approaches to yielding that responsibility. Personally, being familiar with the field, I think it's far from pigeonholing people, but I noticed that in the quantum community, we don't even talk about whether we address quantum information, quantum communication, quantum sensing, quantum computation. So how do you address the responsibility of actually rendering people future ready, empowering them to take up diverse kinds of careers through quantum?
Thank you for that question. Let's start with Yancho.
Thank you. Question. Okay, like any new technology that we want to include in curriculum, now the idea is to include also the quantum technology together with IT technology, AI technology. So, of course, this will replace something else, but the curriculum should be updated and should be in time with the development of those technologies.
Dr. Yeh?
Thank you. I think in where the country I'm from, I understand that more because I grew up with the U.S. educational system. So in the U.S., education is a state, right? And so because for the most part, education is a responsibility and done by the states, then each state chooses a different strategy and curricula. So geographically, there are some states that focus more on quantum, where there's more career opportunities in quantum, and then other states focus on other aspects of STEM. So at least at the state level, that's something that is expected. And as we're taking away, it depends because the US curriculum is very rigid. One thing I should mention is that in recent years, the US nationally has pushed this rehaul of the national education curriculum to focus on NGSS, next generation science standards. And this is a more holistic approach to the thinking behind how to be a scientist, training students to be scientists, rather than focusing on maybe more rote memorization and mastering of specific technical skills, so the bet here is that the translation of how to think about science and asking questions, inquiry-driven analysis, and more interdisciplinary focus of the education system holistically, rather than like memorizing a lot of very specific concepts that might not translate as directly to direct career opportunities in the future for the students is a trend and a national effort in recent years done by the US. So I think quantum fits perfectly into this vision because quantum itself is the most interdisciplinary new topic and area that it's a really big opportunity for education, I think, in all regards with this, because I think quantum, a lot of people in quantum information science and technology don't have physics backgrounds. A lot of my colleagues at Quantinuum has no formal physics training. They're from maths or electrical engineering or computer science or chemistry, material science. A lot of skills are needed to build a new type of computer. And we're seeing that in practice, that there's no one route. In fact, there's so many different routes to being in the field of QIS.
Dr. Suen, please. Thank you.
I hope I'm answering Angie's question correctly, but I take a much more liberal approach in this, in the sense that I think education is a two-way street. Our role, in my opinion, is to provide whatever opportunities and the most realistic things that we can provide in terms of accessibility. But at some point, I think the students have to decide for themselves if they want to invest a bit more time in quantum versus AI or some other things. I guess to play devil's advocate, I think the students themselves have to make a little bit of decision themselves.
And that's, but not the least, Dylan.
Okay, I said it's a bit contradictory to what they mentioned. A bit of background for everyone: the curriculum design in the Philippines is quite centralized, especially with the undergraduate programs. So, for example, we are going to discuss this a bit later in the working group too. The Philippine curriculum, for example, in engineering has 54 core courses and only 5 elective courses wherein you can fit in other things. So that gives us a bit of a disadvantage in how do we improve fitting in quantum or any other emerging tech in that fact. So that's something that we need to be a bit creative for. So we can't dwell into fitting them in individual syllabi or looking at different offering of programs instead of courses, because that's a bit of a constraint problem for us. So that's something that we might need to consider. We're going to talk about that later. So if you are interested, guys, we will be dwelling more into that kind of problem in working group 2 later.
Well, there you have it. We've just heard 4 unique, grounded, forward-looking perspectives on how to grow the ecosystem of quantum learners, educators, and advocates. It's clear that quantum education is no longer a side quest, it's a frontline mission. So to our panelists, thank you for your time, for the insights and and for making quantum education or quantum science something people can see themselves in. So to everyone in the room, whether you're an educator, policymaker, researcher, or a student, you're part of this unfolding story. So maraming salamat po, and I hope this conversation inspires more collaboration in the months ahead. Thank you and enjoy the rest of QISTCon.
All right. Thank you so much for that insightful discussion. May we request all the speakers and the moderator to stay for a quick photo opportunity. Calling all the documentation team to take a photo for this quick final discussion.